We've seen the Maclaurin series where we expand a function in powers of x. This is most accurate near x equals 0. But suppose we wanted it to be accurate near a different value of x. We can expand around a different value of x. We're generalizing the Maclaurin series, and it's now known as a Taylor series. So a Taylor series, we're expanding a function not in powers of x, but in powers of x minus a. So let's imagine that we want to expand a function using a Taylor series, expand around x equals a. What we mean by an expansion around x equals a is that we will be evaluating the function and the derivatives at a, and we have powers not of x, but of x minus a. So here is our formula for the Taylor series. The Taylor series expansion of f of x around x equals a. F of a plus x minus a times f dashed of a plus x minus a all squared over 2 factorial times f double dashed of a plus x minus a all cubed over 3 factorial times f triple dashed of a, and so on. We can see how this is going to keep on going to further terms. This is the Taylor series expansion. Of course, if we set a to be equal to 0, we recover the Maclaurin series. Let's see an example of the Taylor series expansion. We want to expand the function 1 over x around the point where x is equal to 2. The first 4 terms in the series, and having done that, we want to estimate 1 over 2.1. Here is our Taylor series formula. We have the function here, f of x is 1 over x, and we're being asked to expand around x equals 2. Therefore, that's our value of a. We'll work with a is equal to 2. We'll evaluate the function when x is equal to 2. We will have powers of x minus 2. We're going to have to differentiate the function. So let's rewrite f of x as x to the minus 1. So we'll have that our f of a, which will be f of 2, that is equal to 1/2. Then f dashed of x is minus 1 times x to the minus 2. So f dashed of a will be minus 1 over 2 squared. That is minus 1/4. The second derivative will be minus 2, that's 2, times x to the minus 3. So f double dashed of a, f double dashed of 2, will be 2 over 8. It will be plus 1/4. The third derivative, 2 times minus 3, that's minus 6, times x to the minus 4. So the third derivative at a, minus 6 over 16, or minus 3 over 8. We could continue, but we're asked for 4 terms in the series. This will give us 4 terms. So let's write it out now, using the formula here. F of x will be approximated by f of a, well that is 1/2, plus x minus a times f dashed of a. So x minus 2 times minus 1/4 plus x minus a all squared, x minus 2 all squared over 2 times 1/4 plus x minus 2 cubed over 3 factorial, which is 6 times minus 3/8. And so on. Well, we can tidy it up a little bit. A half minus a quarter of x minus 2 plus an eighth x minus 2 all squared. 3 and 6 will partly cancel. We'll end up with minus a 16th of x minus 2 all cubed, and so on. So this is our Taylor series expansion for the function f of x is 1 over x around a equals 2. What we don't do is expand the various brackets and combine the various terms. Each term exists as a term in its own right, and near x equals 2, you'll see if x minus 2 is small, this will be small, this will be smaller still, this will be smaller still. You're able to see the progress towards smaller terms. And indeed, we're asked to do something like this. We're asked here to estimate 1 over 2.1. Well, we have our function, which gives us 1 over x, so we just set x is equal to 2.1. So all those powers of x minus 2, x minus 2 is equal to 0.1, and putting this into the function, we'll get that f of 2.1, well, we know that this will give us 1 over 2.1 from the definition of the function here, but from the series here, we get that it's approximated by 1/2 minus a quarter of 0.1 plus an eighth of 0.01 minus a 16th of 0.001. And we can continue. But then 0.5 minus 0.025, getting smaller, plus 0.00125. Every term gets smaller really quite rapidly. But we end up here, when we put into the decimals, we get 0.4761875. Now I've written it to a rather ridiculous number of decimal places, just making use of all the decimal places that come out of the terms that are here. Of course, it's not difficult to work out 1 over 2.1. Let's try that, and let's compare the results. So let's try 1 divided by 2.1. What do we get? 0.4761905. So the exact value, I put exact in quotes because, of course, however many places we write down, it is a matter of rounding. 0.4761905, we'll say. So you can see that we get 4 decimal places the same, and indeed the fifth, if we were to round to 5 decimal places, we would get 5-figure accuracy. Of course, for a function like 1 over x, it's not greatly advantageous to calculate using a Taylor series, but there are many functions where it is much easier to make use of the Taylor series than to evaluate the function repeatedly. And also, putting Taylor series approximations into various calculations and formulae allows that to be taken to the next stage more easily. So let's see another example. We'll take the function f of x is equal to x over 4 plus x squared. We're going to expand this as a Taylor series around x equals 1 up until the term in x minus 1 to the power 4. Now, rather than write out the detail of every single term, here is the calculation that we do. Each time we differentiate, we use the quotient rule. You can see that we have 4 plus x squared to a power on the bottom. Each time we use the quotient rule, there is a little bit of cancelling going on. There's a bit of manipulation there. Each time the power on the bottom increases, the top gets that bit more complicated, but you can see 4 plus x squared, well, that's 5. We've got powers of 5 on the bottom line. We're able to evaluate f of 1 and the various derivatives at 1, and when we put them all into the series, this is what we get. A fifth plus 3/25 of x minus 1 minus 11 over 125 times the square, plus something involving the cube, and something involving the fourth power. So that's what it looks like expanded as a series, but let's now take a look at various graphs of the function and the Taylor series. We have here expanded up until the power in x to the 4, but we can continue. Here we see in black the function x over 4 plus x squared. And here we have the first few Taylor series approximations. If we just take 1/5, this is what we have in red. It's equal to the function here, but it's not a particularly good approximation anywhere else. But it is a starting point. In green, a fifth plus 3/25 of x minus 1. This is a first order Taylor series approximation. It's equal to the function at 1, and it has a derivative equal to the derivative at the function at 1. It is the tangent at 1. If we then add in minus 11 over 125 times x minus 1 all squared, we get the one in blue. It has the correct curvature at this point. You can see it's a good approximation between around, well, 0 and 1.8, but then go a bit further away, the curve, the function, and the Taylor series diverge from each other. But we can calculate more terms in the series. Here we can see, in black once more, the function. We see the 5th order Taylor series in red here, and the 10th order one in green, and indeed the 20th order Taylor series in blue here. Those higher order Taylor series appear to do an excellent job of approximating the function, well, if we take the most extreme one, between around minus 1 and 3. But once we go past minus 1 or 3, it almost seems like the higher order we use, the more rapidly it diverges. And indeed, we are talking about a convergent series for the parts here, but divergent here. We actually have a radius of convergence for this series of just a little bit greater than 2. And indeed, we can vary the order, the number of terms we have in our Taylor series approximation. Once more, we see in black here our function, x over 4 plus x squared, and then varying the order of the series starting from 0, going through the various cases that we've already seen. Fifth order approximation, going up to about the 20th, indeed 21st order approximation. You can see we've got excellent convergence between -1 and 3. We go up further, say, well, here we have it to 48 terms, but all we can see now is that no matter how many more terms we use, we're not getting significantly past -1 and 3. And once we go past those values, it does seem to diverge quite rapidly, even if we were to take the 100th order Taylor series.